Riemann sums and area. If you have not watched the video on the introduction and overview to integration, I suggest that you go back and watch that now before you watch any of the videos in this section on integration. Let's consider a function f of x on the interval a to b. I'm going to draw a somewhat simple, not overly simple, but not overly complicated function f of x. And I will choose some values a to b, like this. Now our goal would be to find the area beneath the curve, really the area between the curve and the x-axis. How can we do that? Well, instead of finding the area, let's try to approximate the area. Now, what kind of shape could we use to approximate the area beneath the curve? Lots of different shapes, but in this case, we're going to use rectangles, where the area of any rectangle is height times base. And if you watch the introduction video, we saw that the height of our rectangles would be f of x, and our base would be delta x. These approximating rectangles are called Riemann sums. That is, the summation of the area of the rectangle will be called a Riemann sum. Now, Riemann is the name of the person that we named this after. I would say who developed this. But I like to think that R stands for rectangle. It doesn't, but sometimes it helps me or helps students remember what we're doing. Let's break down our interval into subintervals like this. And we want to draw rectangles, not to give the exact area, but to approximate the area. Well, on each subinterval, there are many places that we could use to find the height. I could start here on the left side. It could be anywhere in between. That is, I could pick any of those points at which I could find the height to get the rectangle whose base is delta x. The question becomes, which of those x values do I choose? Well, if I want to do a left Riemann sum, I'm telling you which x value I want to choose. And the x value I want to choose is the one that's on the left side of the subinterval. So I'll use the left side to go up and get the height of my function. How about on my next subinterval? Well, same thing. I choose the value on the left of the subinterval to go up and get the height. That is, I go up to my function, and that becomes the y value for the height. And on each subinterval, I do the same thing. I pick the left side to go up and get the height. My next subinterval, I choose the left side to go up and get the height, etc. One more there. I'll do one more just to finish it off. So the name of the Riemann sum is telling you where on the subinterval we should go, or which x value on the subinterval we should use to draw upwards to get the height of our rectangle, whose base is delta x. Well, the next type of Riemann sum we could do is called a right Riemann. So let me draw my function again. Try to draw relatively the same. It's probably a little bit different. And I'm going to break my interval a to b into subintervals. And we want to do some right Riemann sums. let's look on our first subinterval. Which x value should we choose to get the y at that x value? I'm telling you, go to the right of the subinterval. So this would be the right side of the first subinterval, and we'll go upwards to get our y value to draw a rectangle whose base is delta x. How about the next subinterval? Well, the right side. You get the idea. Every time we want to start on the right side of the subinterval to go up and get its height. Like that. So this name is telling you where you want to go on the interval to draw the height of a rectangle. Let's look at one more. Draw the picture again. Somewhat similar. Pick an A and B. And I'm going to draw bigger subintervals this time. So bigger delta x, just so it makes it a little bit easier to see. And this last type I want to do is called a midpoint Riemann sum. I bet you can guess where I should go on each subinterval to find the height. Now again, I drew these subintervals bigger just to make it easier to see what's going on. Not that a Riemann sum, when we're doing a midpoint, naturally has bigger subintervals. But it simply says in my first subinterval here, I'm going to use the middle point to find the height of my first rectangle. And then on my next subinterval, where do we go? Well, we start at the middle point and go upwards to get the y value. And on each subinterval, we use the midpoint of the interval to find the y at that particular x. Now there are lots of other types of Riemann sums, but these are the three main ones that we see in Calculus 1. I want to do a numeric example with you. Draw a table here, and I'm going to put down some x values, and then we'll put down some y values beneath it. As we'll put some function values in the table. And we want to approximate the following integral, f of x dx. This notation we talked about in the introduction video. And we're going to approximate it, and let's use Riemann sums, that is some rectangles, to approximate this integral, this area under the curve. I'm not going to draw the function itself. You can if you'd like to. But I think we can do this algebraically without a picture. And the following will be my subintervals: 0 to 2, 2 to 6, and then 6 to 12. And we're going to start with a left Riemann sum to approximate this area. Well, I know the approximation is going to be sum of the areas of rectangles whose height is f of x, whose base is delta x. So what is the height of my first rectangle if we're doing a left Riemann sum? Well, the left Riemann sum says we're going to look at the left x on the interval to find the y value. So it's going to be 3. Now 3 times what? Not times x, but times delta x. Be careful there. That's the area of my first rectangle. How about the next subinterval? we use the x on the left side, that is x equals 2, to find the height, which is 5. That is to find the function value. Now times not x, but delta x, so times 4. On the last subinterval, we once again use the x on the left side to find the function value or height, which is 8. And then we multiply it by delta x. Not x, but change in x right there. And if we were to put this all together, we get 6 plus 20 plus 48 equals 74. How about a right Riemann sum? Again, these are going to be rectangles, that is areas of rectangles, that we will use to approximate the area under the curve. For a right Riemann sum, we're going to look at the right side of the subinterval, that is the x over there, which is x equals 2, and we're going to use the y value or function value to get the height. So in the first subinterval, using the right side, we get the height as 5, and then delta x is 2. Next subinterval, we look at the right side again. So the right side is x equals 6, and f of x equals 8. So the height is 8, and the base, delta x, is 4. Do it again. Right side of the subinterval is x equals 12, which gives us y equals 12 as well, times what? Not times x, but times delta x. And if we add these all together, we get an approximate area of 114. Now, which one of these is more accurate? Truth is, without more information, we don't know. But let's do our final Riemann sum, and let's do a midpoint Riemann sum. How do we find the height? We use the middle x on each subinterval to find the height. So the middle of the first interval is x equals 1, and the function value or height there is 4. Delta x is 2. I'll do the next two more quickly. Use the x in the middle, x equals 4, to get the function value or height. And then delta x, not x, but delta x, because 2 to 6, the change is 4. Final midpoint, the middle x is 9, the height is 10, and the change in x is 6. And then if we put all of these together, we get an approximate area of 92.